Finally, we will set up the basement structure. Here, I will show you how to set the road, carry out the design, and create the underground structure and drawing. nGen provides a variety of members since it pursues the model-based modeling for design and drawing. Among them, we will take a look at the footing and the outer wall of the basement. Midas engine provides mat footing, isolated footing, and strip footing. Besides, we provide tools to arrange piles and pile support easily. There are two methods for footing design in nGen. Rigid design is the method that designs the footing with the same reaction force, assuming that it has infinite rigidity. FEA design is a method of performing design based on the result of FEA analysis. Two methods can be applied for mat footing and strip footing. And only FEA design can be applied for isolated footing. Soil spring and pile spring are provided to check the support of the footing. Spring property provides three types of linear elastic, tension only, and compression only. In pile spring, information on the pile diameters for punching review and the allowable support capacity for soil bearing review must be entered, and input the stiffness value for each directions for analysis. Next, I will introduce the pile placement tool. There are three methods provided. The first one is a point-based arrangement. This is a pile arrangement method for isolated footing. And we can easily place it by entering the number of piles and the spacing between piles. And the last step is select a target point. The arrangement shape according to the number of piles is as follows. And the next one is line-based arrangement method. This is the arrangement method for strip footing. If you enter the number of piles, intervals, and set the 2 point, they are automatically arranged according to the gap between 2 points. The third and last is an area-based arrangement method. This is a placement method for the mat footing. It is automatically arranged on the selected foundation member according to the spacing between the piles. Next, I will briefly explain the design of the base plate in nGen. The value, calculated from the base of the column, is used as a member forces for flexural design. The pile footing is the same. In the one-way shear design, it is assumed that the soil reaction force is transmitted directly to the column in the area inside the shear line as follows. Therefore, the one-way shear force is calculated only as of the force outside the control line and reflected in the design. The punching shear design is carried out in the same way. It reflects only the force except for the soil reaction force inside the control perimeter. even if there is a pile, the reaction force equal to the pile area included in the control line or perimeter is ignored and reflected in the punching review. The following is a review of the stability check. Soil bearing, overturning moment, and sliding are leave for stability check. The first is the soil bearing check. The method of review is as follows. I'm not going to explain how to calculate soil bearing pressure here. The stability check for soil bearing is shown as OK or not good by comparing the allowable soil bearing pressure value set in the design parameters to the maximum bearing pressure. In the case of overturning, the sum of the moment acting on the footing and the moment caused by the shear force acting on the column is regarded as the overturning moment. The resistance moment is the weight of the footing and the soil and the axial force transmitted from the column. The overturning moment and the resistance moment divided by the safety factor are compared to check the stability. The safety factor can be entered as follows in the design parameter. Lastly, the stability condition of sliding is judged by comparing the lateral force acting on the column and the frictional force of the soil on the foundation's lower surface. The safety factor must also be considered at the same time and can be entered in the design parameter. In addition, the frictional force is calculated by multiplying the axial force of the column and the load by the self-weight of the footing by the coefficient of friction. And the coefficient of friction can be set directly as follows. Next, we will explain the input of earth pressure. Earth pressure is created as a function of level and pressure as shown in the following dialog box. Factors that affect the functions are ground level, water level, load on the ground, and internal friction angle. When a load function is created and assigned to a 2D member, the load is automatically applied according to the member's level. Earth pressure generation is calculated in the following way. It is applied according to the Jenkins theory. I will leave out a detailed explanation. To apply earth pressure according to the other theoretical equations, you can copy the values calculated according to the other tools and paste it into the table to use them. Earth pressure is applied differently in 3 places: top, side, and bottom. For the top part, the soil weight calculated through the load function and the gravitational load by live load is applied to the slab. For the side part, the lateral load from earth pressure is applied to the basement wall. For the bottom part, buoyancy to the slab is applied, which makes it possible to perform analysis and design reflecting the buoyancy. Finally, design the basement wall. For the previously input earth pressure, design results are provided for each element as follows. When designing the basement wall, it can be uneconomical to place levers identically in all areas according to the largest bending force locally. For economical design, the basic levers are added to the whole basement wall first, and additional levers are reinforced to the area where the strength is exceeded to satisfy the design criteria. Next is the lever. Reinforcing bars can be partially added to design the areas where the strength is insufficient. The design was satisfied due to the increase in the member's strength by adding the additional lever. The method of adding levers will be explained through a demonstration. Then let's look at member modeling, design, and drawing creations for underground structures. First, let's create a basement wall. Select member, thickness, and create as follows. We will create a strip footing at the bottom of the basement wall. Next is the mat footing. Let's fix the overlapping part, and let's combine the strip footing to be considered with the same design. The following is an independent foundation model. Let's select the columns to create the foundation. Next is the creation of the internal slab. Among the groups classified in the model tree, only the basement and slab will be activated. I'm going to delete the unnecessarily created slab. Then merge the slabs. The following is the input for support. Of course, you can use a soil spring, but in this demonstration, I will apply pile spring. As explained earlier, You can easily enter the information through the pile arrangement tool. For the piles in column, I'm going to assign them based on the point-based arrangement. For the basement wall, I'm going to use line-based arrangement tool to assign piles. The next one is the pile arrangement for the specific area. Next, I will enter the earth pressure. First, create a function for earth pressure. Second, select a member. And lastly, enter the load for each direction. Note that when applying pressure on the basement wall, the direction must be determined according to the local axis. So the load direction must be determined by checking the local axis. Now, let's start the analysis and design process. First, create and perform an analysis case. And create a load combination. Then I will check the value of the design parameter and enter the reinforcement for each member. The reason that I cannot enter any value here is that the layer is 0. So change the layer to 1 and enter the value. Create a design case and perform the design by selecting only some of the selected part. The following error occurred because some parts do not have reinforcing bar information. Let's enter the missing information. In this case, the design process is completed successfully without errors. The red part is the member with ng. Let's check the design result. ng occurred in the shear design because the minimum reinforcement ratio is not satisfied. The result of FEM shows that large stresses are generated locally. If we design the whole model based on these large stresses, it will be over-designed as I explained earlier. So in general, we apply the average value over a certain width like this. The width is usually 2 to 4 times the thickness. We will modify the reinforcement information to satisfy the minimum reinforcement ratio. Let's redesign. Then the design of the footing is satisfied. Next is the outer wall of the basement. Looking at the design ratio for MXX of the outer wall, it exceeds 1.0 in some part. Let's add rebar for this part. So let's redesign it. You can see that the design ratio decreases, which is less than 1.0. Now let's create a drawing. In the drawing set, check the level of the list. First, I'm going to create a basic drawing. You can see that the basic shape and reinforcement information has been created. Here is the pile layout. Unlike the basic drawing, the plane dimensions and level informations are displayed to determine the location of the pile. Reinforcement for the slab is also created. Now let's create a section view. Create a section view by setting the desired location. Next, we will create a reinforcement map of the outer basement wall. You can check basic level and level informations as follows. Finally, let's create a floor plan for other floor. I think these drawings will be of great help in the creation of structured drawings.